All right. Well, hello, everyone. This has been fun. I enjoyed spacing. We're actually looking into sending a CubeSat to a comet. So that one would be super cool if we could do that. So let me share my screen here. And we good? All right. So I'm going to talk to you about this gigantic ball of stuff sitting in space, and what do we know about how you can construct an Earth astronomically, and some aspects, of course, are from the Earth sciences. When I was growing up, one of the best comics was Calvin and Hobbes. They've been gone for a long time now. But boy, I love this one, and you can read it. I won't read it out to you, but if you haven't checked out Calvin and Hobbes, I highly recommend it. And so, the question about life, why we're interested in the Earth, right? Because we're on it, and we're having this conversation right now, right? And there's the question about where did the planet come from? How was the planet constructed such that we're here? When the Earth formed, was it preordained that we would be here? And then, of course, the big one, are we alone? And of course, I don't know. I teach a class about it, but what I could tell you is this: since 1992, we detected 4,000 planets, around 300 stars. So this number keeps going up. It may be 5,000 now. It's amazing. None of them at present are direct Earth analogs. That is, an Earth-sized planet at one astronomical unit, one Earth-Sun distance away from a star that's exactly the same as our sun. But that's coming. There, of course, are things that we didn't foresee. Jupiter's parked right next to the star. We call them hot Jupiters, and super Earths. So things that are, 1 to 1.5 times the radius of the Earth. And what are those planets, and are they anything like our own, is an open extant question today. And we are observing planetary systems in formation and trying to understand the range of potential outcomes and what might lead to the formation of various types of planets. And going forward, within the next decade, in our lifetime, we will really begin the search for looking for whether life is out there, looking for ozone and methane around these Earth analogs once we find them. And so it's possible that, within the next 10 to 20 years, there will be gigantic headlines splashed out that we detected oxygen in another planet, and that whoever detects it is going to say that we're not alone. I'm doing the formation part, really, okay? And, when you want to think about the formation of life and how we got here, it's really, really hard. And, there's an abiotic chemistry that's happening out there in space and happens on the planet. And then it transitions to reproductive chemistry, or chemistry with memory, that we call biology. That's not me, and that's not astronomy, of course. Rather, we're looking at, what are the conditions that foster life, and what are those conditions from an astronomical lens? Well, you have to have a rocky planet, not a gigantic ball of gas. It has to have the right stuff on it. And it's an interesting question. You have to think about, what does right stuff mean? It has to be the right distance from the star. We know that a key facet is water. So water is one component of the right stuff. And if you're too close to the star, it's too hot, and the water is all in the atmosphere and will likely get lost over time to space. And you'll turn into Venus. If you're too far from the star, you'll be an ice world, right? So you have to be at the right spot for water to exist as a liquid on the surface. And it has to have a stable climate. And I'm not going to talk about that, but that's another very important facet that one could get into. And so what are the right materials? Of course, the right materials is the stuff that we're made of. And we're mostly carbon, hydrogen, oxygen, and nitrogen. And of course, the hydrogen and the oxygen is H2O. We are mostly water, but carbon provides the backbone of the chemistry of life, and nitrogen is a key component of life's chemistry. And of course, there's other very important components as well, such as phosphorus. And the neat thing is of these elements, the carbon, the hydrogen, the oxygen, the nitrogen, they're mostly existing in the gaseous state, and so we can observe them astronomically and try to understand, well, where is this stuff, and how do you follow the material that we're made of versus time? And so broad brush picture from astronomy is that things start out in these diffuse clouds of gas. They're mostly molecules, and I'll show you that a little bit. They're huge, and portions of those gas clouds collapse. And those gas clouds also have solids in them. They're tiny. They're 1/10 of a micron in size. Mostly they're made of silicates. And those tiny little silicates are the seeds of Earth-like worlds. You'd break the Earth apart. The Earth was once a bajillion tiny little pieces floating in space that was collected together via a collapse down to a star and a disk, and then the surrounding envelope that gets dissipated away with time until you get a disk and the star, and the planets are born in the disk. And that explains why all the planets in the solar system orbit in a plane, except for Pluto, which of course we kicked out of the planetary brotherhood, and that's one of the reasons why, that it wasn't orbiting in the plane. And then you get this planetary system. So this is the constellation of Orion. It's one of the key things that brought me to astronomy. And molecules out there in space, they rotate and they bang into other molecules, and it puts them into a higher rotational state, and they relax down to the ground state, you know, sort of sitting on the couch, munching on some popcorn state, and they emit a photon of light. And we can observe that photon of light. So you're looking at the Orion constellation now with carbon monoxide eyes, all right? And so this is what we call, we're very illustrative in astronomy. This is a giant molecular cloud. It's composed of gas, it's mostly molecules, and it's giant because it's massively huge. That's 100 light years in size, which is a bajillion kilometers, right? So it's these molecules, mostly hydrogen, but then trace species such as carbon monoxide. We can measure the temperature of these objects, which is, you know, one of the things that I started out when I got my PhD. They're only 10 to 20 degrees above absolute zero, so minus 263 degrees Celsius. So there are molecules that we can use as basically thermometers. It's really, really cool. And we can also measure mass. And this particular thing contains enough material to make over 100,000 suns. So this is where we are today. The best instrument right now to look at planet formation is the Atacama Large Millimeter Array. You heard from Michael Meyer earlier talking about the James Webb Space Telescope. That's going to be the next big thing on the scene. But ALMA is an array of telescope 64 working in concert. And what you're looking at here are disks where planets are being born right in front of our eyes. They're all in different orientations in the space, right? Because there's no preferred orientation in the galaxy. And their structure, you can see here that there are some with gaps. And what we think is carving out those gaps is planets that are hidden, and they're interacting with the materials and pushing them aside. And what that was actually you're looking at here, this isn't the molecules emitting. This is the emissions of tiny little millimeter-sized particles that are absorbing starlight, basically pebbles. So you're looking at pebbles in space that are re-emitting reprocessed starlight. They're absorbing energy from the star and re-emitting at millimeter wavelengths, where I'm observing it with the Atacama Large Millimeter Array in Chile. It wasn't me. This is a postdoc here at Michigan now, Jane Huang. You can see as I go through this litany of structures, there's lots of gaps here. This one's a continuous disk. Here's a spiral. We think that's also caused by hidden planets. And so we could actually look and try to follow planet formation in action. And those are the solids. They're the seeds of the terrestrial worlds. And here are the gases. These are the gases, the volatiles, the volatile elements, the carbon, the hydrogen, the oxygen, nitrogen, mostly either in the gas or the ices. And we can observe them when they're in the gaseous state. So these are different objects going this way, all right? And these are different molecules in each of these different objects. So this is one source here. And you can see different molecules. Here's formaldehyde in space, stinky, smelly formaldehyde in space. Cyanoacetylene, whatever that is, right? C2H, you see these, there's rings, tremendous structure. And what we could do is we can observe the content and measure the content and study the chemistry and ask, well, what's happening? And what's happening is this chemistry is making water and it's making organics. And most of those things are frozen as ices and ready to be supplied to a terrestrial planet as ice coatings on those tiny little silicate particles that are the seeds of young Earths. So we can also observe water. Here's the Orion constellation, a more prettier picture. This is a gorgeous, gorgeous image from one of the ESO telescopes, the European Southern Observatory. In Orion, this is the belt of Orion. This is the sword. This is the Orion Nebula. You're looking at basically, I don't know, in this image, probably a few thousand baby stars that were born about 1 million years ago. And right here, this is the youngest one. And if I point my telescope at it, I can image this. This is a spectrum, one of those. This is the emission of water in space saying I'm here. And that particular region is a water factory. That's 1,000 oceans sitting out there as vapor in space. Again, chemistry of space makes water and organics. So what happens is you take these tiny little millimeter-sized particles, they have a big party, and they make kilometer-sized bodies that then accrete more of these tiny little pebbles until they get to Mars-sized bodies. And then the Mars-sized bodies bang into each other until you make an Earth. And so here we are. We made an Earth, that's great. We have this wonderful, gorgeous, beautiful water world. But actually, if you look at the Earth, we have a tiny amount of water, less than 0.1% of the Earth is water by mass. Well, here we are again, Earth, all this beautiful green carbon stuff. No, the Earth is a carbon poor world. From the amount of carbon that was available, we received 1 out of 1,000 atoms that was present. The nitrogen was 1 out of 100,000 elements. We are a silicate rock sitting in space with a tiny sprinkling of carbon, nitrogen, and a little bit of water. Yet we're still here. All right, so that's one of the frontiers in front of us as astronomers, is how common is this? A planet that doesn't have that much carbon, which probably is a prerequisite for life, because I suspect if you get too much carbon, you'll have a CO2 dominated atmosphere and be Venus. And of course, we don't know that right now, but that's part of the landscape in front of us. Now, how did this come to be? Well, it came to be because of this, that there is the sun here, and here's, distance, the proto-Earth, proto-Mars, proto-Jupiter. It's hot near the sun and hotter close to the stars. So any of those tiny little pebbles that I was showing you the emission from, they won't have water on them. They'll just be tiny pebbles. If I go a little bit further away, it's cold enough, water will condense as ice, and you'll basically have icy comets. And we think that that's the outer parts of the asteroid belt heading out in Jupiter. This is the snow line. So the Earth formed inside of the snow line. That's why we're so water poor. It's also probably why we're so carbon and nitrogen poor. So then how did we come to be? And so to show you how we got our carbon and nitrogen and oxygen from water, I'm going to show you a couple movies. And one of the key things of the movies is eccentricity and inclination. So here I am in a bunch of bodies orbiting around the star, and they bang into each other, okay? They come close to each other. They have a gravitational interaction, all right? And that throws one of these things onto a different orbit, changes its eccentricity, which allows it to perhaps interact with something else at some closer distance to the star, or maybe a further distance from the star. All right, or it may get thrown to a different inclination, and that's what I'm showing here. So why am I doing this? Well, because I'm going to show you some simulations about how you make an Earth. And what I'm showing here is inclination and eccentricity. So this is distance from the star, and these things are sort of color-coded based upon their water content. There's slightly more water out here, slightly less water out here. And I'm going to let these bodies, they're basically kilometer-sized planetesimals, and they're going to gravitational interact with each other over time. And you can see under this circumstance, everything pretty much forms in place. It gathers everything from where it was born. And under that circumstance, the Earth would truly form dry, and I would not be speaking to you here today. So instead, what we think happens, and this is the prevailing theory, we don't know if it's right, is that there were gravitational interactions with Jupiter that shook the architecture of the forming solar system and brought water that was present out here in these blue objects. So now the scale, scale has changed here. This is 1 AU, this is the Earth-Sun distance. Now you're out here, here's Jupiter, okay, and 2 AU3, this is where all the water and the carbon is. All right, now because Jupiter's present, you can see lots of things are interacting with each other. That's what's happening when you get to these higher eccentricities. That means that things are interacting, and you can actually see the resonances with Jupiter's orbit. That's what's going on here. But interactions with Jupiter and Saturn cause, we think, Jupiter to move inward and then outward again. And that re-sculpted the solar system. This is the so-called grand tack theory. And under that circumstance, you basically took a lot of material that was out in the near the snow line and brought it inward and supplied it to a young Earth. So now that when material form here at 1 AU, 1 Earth-Sun distance, instead of being orange like they were before, they're sort of yellowish or greenish. They have a little bit of water, a little bit of carbon, and they're us. So what does this mean? It may mean that having a Jupiter present in the system where it is could be important for the formation of life. We don't know that, right? And we're gonna have to figure this out. Some worlds may get more carbon, nitrogen, oxygen, some less, and we don't have a clue as to where we stand in this construct. And so what we're gonna do, of course, is astronomers are gonna go off and, like I'm doing here, and study formation and track the materials of life versus time, if I can. And then other astronomers are going to go out and observe those super Earths and observe those Earths and see what their content is. And then we're going to try and cross-correlate, understand how that came to be. I'll stop there. Thank you.
Awesome. Thank you so much for the very interesting talk. I don't think I've ever heard much on the formation other than, the very, basic thing you get taught in high school, which it's very refreshing to hear that we know much more than that. We do have a couple questions in the chat. I'll go ahead and read some of them off. The first one being, are we looking more for the necessary resources for life rather than just detecting other life, or so that we can possibly inhabit them, or is there other kind of conditions that we're looking for?
So what we're trying to do, okay, is we're trying to understand. All right, I don't know if I'm going to answer. I don't know if I understand the question correctly, but what I'm trying to do is follow the water. When did it form? How much of it formed? And how much of it gets onto a planet as it's born, with different assumptions with respect to the architecture of that forming system, the star. There could be a star more massive than our sun, less massive than our sun. All that matters. Follow the carbon. What are the primary carriers of carbon? And how do they get supplied to a young forming planet? And then on the flip side, what they're going to be doing is observing the atmospheres of Earth-like analogs, okay? And is every planet that we look at going to be a CO2 dominated atmosphere of Venus? Or are we going to find objects that look like our own, which have a nitrogen dominated atmosphere with some CO2, of course, and then ozone and methane? And, you know, how these two things play to each other, that's the beauty of science, right? There's so much work to be done, which is why I love it, right? I'm not going to finish. I'm not going to solve this problem. I'm just going to contribute. And it's, you know, the next generation that's going to continue and build up this knowledge base.
I think just to go off of that question and maybe clarify it a bit, I think part of that question was to trying to get at, like, are we looking for these materials of life, as you called them, in order to just detect other life, or to potentially actually someday inhabit those planets?
No, yeah. So all this, everything we're looking at, so the closest forming planetary systems are about 300 light years away, right? And so you're the engineers, right? You could figure out we're never going to get there, right? We could barely get anywhere in our own solar system, although we have gotten pretty far. In our solar system, of course, there's exotic and interesting environments that are worth exploring from the perspective of the potential for life, and Mars first and foremost, and then Europa and Titan. But we're not going anywhere. It is the case, however, if you want to think about resources, right, that the asteroid belt is rich in resources.
All right, thanks. I hope that answers the question that was in the chat earlier.
One more question that was thrown in the chat. Could you show some more light on the change of mini planet orbits, their shape and inclination while merging with other mini planets? Because won't it affect the orbit parameters of both objects?
Oh yes, yeah. So that was just each object was doing their own little thing. Now, one might be a big one and be less affected, right? But and it depends upon how they come. What I was showing you were basically N-body simulations. So they put in like 100,000 of these things, and they just let them gravitationally interact with each other. And each object is gravitationally affected by every other object in the simulation, including the sun, right? And then it's modeling all those gravitational interactions at once. It's a common thing in astronomy for about the past 15 years or so. And the question is, how do you display it? And that's one representation, is what I showed you, is eccentricity. And eccentricity is a tracer of the interaction. Okay.
All right. If there's no more questions right now, if anyone thinks of anything, please throw them in the Slack, or can they email you at all to?
Of course.
Right. So feel free to email him as well.